Good afternoon. I wanted to follow up with some other types of videos that I presented a while ago that I was still thinking about from more of an algorithmic perspective and maybe some upcoming work or some other types of related projects that I've been thinking about, which has primarily been focused on performing time evolution and quantum computing. In two of my previous videos on the channel, I drew the viewer's attention to a lot of scripts that I'd used of the format that I'm going to show in this type of presentation, in which I pretty much was interested in making use of some type of open source package from Google Quantum AI, which, as an open source Python package, it allows us to perform time evolution on quantum circuits, and it actually helps us determine whether the algorithm can be efficient in some sense by some arbitrary standard without putting noise on the quantum system, which is, pretty much idealizing the state and the quality of the measurements that we can extract from this quantum circuit. And in those previous videos, I drew the viewer's attention to a lot of different types of areas and how this relates to algorithms that could be used in quantum computing if next generation hardware actually becomes available, and whether it's as fault tolerant or as absent with, or more impervious or more difficult to, ruin with the presence of noise. Because that's really much a very big issue. What comes into play with quantum computing is that when you're trying to determine whether, say, for instance, how some recent papers in the literature have determined or asked whether integrability holds for quantum circuits, or whether even other types of desirable properties hold for quantum circuits, which would hence allow us to perform time evolution, which from an algorithmic perspective would lead to wider and broader business adaptation of quantum computing. It's really contrary to the case of what we've seen now. And I think that a lot of people are coming to realize that, because so many papers have been talking about how, say, for instance, different types of use cases or near-term applications of quantum computing will, pretty much prove to be revolutionary, and that they would, permeate or, influence the operations of businesses. And obviously, rather than, maybe some niche applications in finance in Europe, as I've also talked about in my channel, that doesn't necessarily seem to be the case. So, you know, I'm just showing all this so that we can keep in mind what would be the limitations to this code, and how would someone try to look up to build future, or further or additional complexities into a quantum system that they're trying to time evolve, if, they were actually looking at some next generation device that would hopefully be used sometime in the near future, if it's primarily developed by the leader in the industry, which in my opinion at the current time is Google Quantum AI. So, like we've been mentioning, is that the super KdV equation, the super Korteweg, De Vries, if I'm saying those names correctly, I'm sorry if I'm not, equation, it's very much related to a previous PD that I had exhibited or talked about on the channel, which is relating to the Kamasa home PD. As I had alluded to, even though it was a few weeks ago, to the viewers in that type of presentation, in that overview of the code, you always have to start out running your quantum algorithm by looking at instantiating some quantum nonlinear processing unit. And as I had alluded to in that type of presentation, it's very much dependent upon how many, qubits or how many expectation values appear in a cost function that you're looking to optimize over, which is also playing into classical computation, because you have to make an appropriate choice of an optimizer. And in this case of the quantum nonlinear processing unit for the super KdV equation, because I was kind of coming at it from a perspective of Kamasa home and wave propagation or shallow wave propagation, in which I was trying to pass either sinusoidal initial data through the ansatz, through the ZGR QFT ansatz to the system, as we're at the beginning point where we're just starting out the time evolution. It very much carried out and helped me study nonlinearities for other systems, which I kind of alluded to in that video. But there are kind of so many different ways that you could take this code, that even looking at some parts of the code which are similar and different can impact the time evolution, and hence the quality of the measurements that you're wanting to extract from your quantum circuits that you're encoding with a classical optimizer with the cost function, which is a superposition of expectation values. And in this case, even in these highlighted terms I highlighted just the first three terms that appear in this quantum nonlinear processing unit, which is a portion, like I had mentioned, a portion of the quantum circuit that we're going to do so that we can extract the measurements. And the quantum nonlinear processing unit is very important when we're running these types of algorithms because when you when you're looking to make use of the quantum nonlinear processing unit, you have to encode the expectation values from specific nonlinearities, either exactly the same as whatever is in the statement of the PDE or very close to the same. And that's important because when we're looking at how we're going to be encoding expectation values and how this relates to the time evolution, like how I'd mentioned for the Benny-Luke equation, as the longest PDE that was given in that paper from the expectation values that I analytically derived and I worked out from taking cross terms from products of different nonlinear, nonlinearity terms in the Benny-Luke equation, it can pretty much make it something that's very difficult to time evolve on, current, near-term devices because of the number of expectation values, which is influencing the classical side of optimization because you have to specify a cost budget or, a budget parameter for your optimizer, which pretty much determines how long the optimizer will run for. And now that we're able to exhibit how different types of these expectation values are coming into play and sorry. And now that we have to have a few of these expectation values into play, it really demonstrates how we can, as I had alluded to, make use of the same general construction in which we're looking at initializing components and pieces of our quantum circuit with grid qubits, from which we also have to specify an ancilla as well as being able to append a Hadamard test along each one of these circuits, which is going to comprise components of the unitary transformation that we're performing in different states. And in particular, as we look in additional expectation values, which we have to specify for the quantum nonlinear processing unit for the super KdV equation, we can see that even from this next collection of expectation values that I've highlighted, namely 3 to 6, we're looking at higher order nonlinearities. It's given by the fact because when we're looking to construct an expectation value, which is even another aspect of running this quantum algorithm that I didn't necessarily allude to or speak to in my previous presentations on the topic, is that basically you have to try to look to make Brockett states, and from the possibilities of Brockett states that you can construct, you can think that in the first position of the expectation value for the bra portion of this expectation, which is going into a cost function, you can have like psi or psi u, some term like that, where psi can maybe represent the time evolved state of the solution of some partial differential equation, as well as given by the fact that the other possibility for what can even occur in a ket term can be a psi u, which is whatever the solution state was in the previous time step. So once you're able to distinguish these types of quantum values that you have when you're looking to perform time evolution from different types of expectation values, then that can really help give a more clear understanding of how it would build up each one of these expectation values, which one is going to be making use of when you're trying to perform the time evolution. And I mean, that type of perspective, even from another perspective, from another applied math point of view that I didn't really emphasize in the other videos, it's really important and interesting because when you're trying to initialize different components for these quantum circuits that you're trying to time evolve, when you're able to think about it and understand of it more from the fact that you're trying to just generate different collections of parameters for solution states, which are ultimately representing some types of factors that you extract from a wave function, from a solution state wave function, which is some candidate solution given some initial condition that you're passing to the PDE. It really simplifies things and pretty much boils it down to the fact that you're just really trying to generate new sets of parameters one time step at a time and reiterating this procedure many times. And rather than the sorry, 1 second, guys. These people are just leaving and it's their car. Okay, sorry about that, guys. Sorry about the noise earlier. And these the additional expectation values that we have to specify for these types of circuits, they're really exhibiting how the super KdV equation or even other types of structures of PDE can come into play because generally when you're just looking to make expectation or analytically drive expectation values that you're going to code up for some cost function that you're looking to classically optimize, in the case of the super KdV equation, because it's different than other equations, which I'll allude to more later on, is given by the fact that you really have to potentially you have to couple two optimization routines together, which is also very realistic and helpful for the perspective of quantum computing because in all reality, say if you want to be, a proponent of adapting quantum computing and say operations research or other types of more difficult or, more complicated business functions, then there can be several parameters which need to be optimized at the same time. And you can try to bottleneck, maybe trying to constrain the range of parameters that you would want to that you would want to satisfy from a constrained optimization scheme from one of the constraints and then kind of let the other two constraints freely behave and determine which type of readout you could obtain from that. So yeah, I think that just having also that perspective into mind, and namely the constraint cops optimization procedure is a little bit different because from this specific constraint optimization procedure, we have one cost function which we're first optimizing over, which has 19 parameters, whereas the second cost function has 30 parameters. So it's kind of interesting to see about, namely, if we maybe start without any types of constraints from the cost function, which is dependent upon 19 parameters, in comparison to the second cost function, which is also still playing a play in the optimization scheme, which has 30 parameters, then there can basically be some type of expected numerical routines which we can expect to be able to extract meaningful measurement from. Sorry, guys, one second. Sorry, I needed a little water. Um, and yeah, so just we can further build upon what our differences in this constraint optimization scheme and how and what's the limits to the nonlinearities that we would expect to be able to extract measurements from, effective or, very pure types of measurements from him. When I mean pure, there are really a lot of mathematical definitions and characterizations of what's a pure quantum state, but pretty much I'm meaning it more in a very rough, applied math sense or applied sense because I'm just trying to see what is the overall trajectory of or the overall behavior of different initial data that we can pass through the ansatz and how this would affect and impact whether we can still perform the associated time evolution task in polynomial time. And as we go further down in the quantum nonlinear processing unit, as I had alluded the attention of the viewer to, we're pretty much ending out the first cost function, namely the cost function, which has 19 parameters in comparison to the second cost function in the system, which has 30 parameters with some expectation values that are either dependent on psi w or psi. So psi w, as I had alluded to, it's really exhibiting how the constraint optimization scheme comes into play because you're incorporating some solution from the other cost function from the other PDE that we haven't yet instantiated in the code. But despite this fact, we can still make use of other types of cost functions and previously defined cost functions, which will initialize the parameters in which will perform the optimization of the second cost function in the system. And this is getting to the fact that to define also the other cost function, which has different types of nonlinearities, which appear in the first cost function for the super KdV system, we're just going to define another cost function. So it's just differing a little bit in the code, which is reflecting some difference, some broader difference, again, as I alluded to, of the time evolution, because we're looking to define a whole bunch of cost function terms and as we can see, even from up to the fifth term that we've given here, We have psi w and psi u. So psi u is just illustrating some previous time step values of the old solution before we're performing the time evolution to either get psi or psi prime, or corresponding to the two solution to the two vectors of extracted measurements from the candidate wave function of the solution for the super KdV system. And what can come into play that I also hadn't alluded to in previous presentations when I talked about the Kamasa-Holm in the Benny-Luke PDEs, the Benny-Luke equations, is given by the fact that sometimes you can have multiples of A daggers or A's. So that just amounts to maybe either trying to experiment with different types of quantum circuit constructions, which can have different types of ansatz, a different number of ansatz terms are appended to the circuit that we're looking to perform time evolution from. And like I'll briefly reiterate, like I talked about in those other presentations, is that I don't have any of the code for the ansatz in any of these presentations for the code because that's not my code. It's just some code that another individual, another very great student from the lab had coded up, which was a very complicated scheme for initializing the solution state. So he was just pretty much giving us some general template with those sequence of operations that he was performing, namely, if I remember correctly, adder gates, I forgot, Fourier transform or inverse Fourier transform, if I remember correctly. And with those types of routines that he was able to perform in that very complicated script, we were able to interface between performing some time evolution and initializing the condition in some appropriate position within Hilbert space so that we can try to maximize the range of parameters which the algorithm is able to produce from this initial configuration. And that way, there's obviously even a thermodynamic component, like, because when you're thinking about statistical mechanics and quantum physics from definitely some upcoming work that I've been thinking about and working on, you always have to think about whether there's some favorable type of configuration of your ensemble that you can perform time evolution on, and what would be the probability or different ensembles of probabilities from which you could be able to extract some measurement from some well-behaved enough state. And as we're continuing to go on in the code, this is exhibiting that, as I had expected and alluded to, the fact that the second cost function in the constraint optimization scheme is dependent upon 30 parameters in comparison to the first cost function in the constraint optimization scheme being dependent upon 19 parameters is really apparent through additional cross terms that we're getting from psi w and psi u, as well as, pretty much psi w or just other types of parameters which are appearing from the last couple of expectation values that we're using to parameterize the second cost function in the constraint optimization scheme. Okay. And now that we have those two terms for the two quantum nonlinear processing units in place, as I had alluded to, there are different types of terms which appear for the two cost functions. So these two cost functions, like we had just been talking about before we got back into more of the details of the quantum nonlinear processing unit, is given by the fact that you have two return statements which are given by two numbers, and the two numbers are given by lambda squared parameters for each of the first terms in the superposition, given by 18 other terms in the first cost function, which have some delta x parameter, where delta x parameter is relating to the square, to the distance or to the size of the mesh of the Cartesian grid, the square lattice over which we're performing the time evolution so that we can extract some measurements. And then there are just other types of ways in which, from carefully working out the cost function for each one of the components of the super KdV equation, that you can have different number of terms and keep track, as well as keeping track of the sign of each one of the prefactors to these expectation values in each one of the cost functions that are appearing within the constrained optimization scheme. And as I had alluded to, kind of, which appears in any type of time evolution is that you really have to think about when you're performing any type of simulation or any type of classification task or test in which you can test out the performance of an algorithm and whether an algorithm is behaving or outputting the type of information that you find useful for whatever your purposes are. You have to really look to maybe scale down the simulation or the computation in the first stage, from which you can then determine if there are broader if there are additional use case applications or broader purposes or broader applications for which you can look to make use of the algorithm. And in the case of this quantum algorithm, because I hadn't really done a constraint optimization scheme, even though it's a pretty simple difference to the code, I hadn't exactly exhibited or, experimented with different initial data that are being used for this optimization. And it really just demonstrates that, in this case, I was looking at 500 time steps. And then when you're looking to perform the time evolution, as a matter of fact, it's great to always have some region of space that's farther out from or that's larger than whatever information or region of space you've timed evolved previously, which is given by how I determine the L parameter, because the L parameter is coming into play because it's going to determine if you know correctly the spacing. And as I specify the ZGR parameters, which are given by the ansatz from the solution, I use a different choice of parameters in this case from what I had talked about in previous presentations, because I looked at an extra qubit to maybe account for additional possible higher order nonlinearities that are associated with the constraint optimization scheme and having to constrain essentially and in essence two cost functions at the same time. And from it's also important to keep in mind that we also looked at making a different use case of the time evolution, and the time evolution that we're performing for the U and V solutions are given in the system for the KdV equation, because um oh, I'm sorry. Um, and then how we're performing the time evolution, because when you have to specify additional parameters, that has to be compensated for with a larger budget for the optimizer. So that really just goes to show is that when we're looking to perform these optimization schemes, having some type of idea about the total number of parameters that we would need to use, in addition to what would be the expected performance of the algorithm on the other side from the constraints that we place on the classical optimization, informs what type of information we can gain from the quantum computation. And now that we're performing these tasks, in this step, like I had alluded to in previous scripts, I just had some lines which were some print statements to show the output of the algorithm at each step. And what this was also demonstrating was that, which was another fact that I unfortunately just hadn't got into in the two other presentations for time evolution, is that when you perform a check wave, it's a function that you're looking to perform on the ansatz after you initialize the ZGR parameters. So that's just really some type of object that we further manipulate after performing the time evolution. Just get a little tricky It can just get a little tricky in terms of what types of parameters you're trying to look to extract from the wave function, which is exhibiting some additional complexities with having to perform a constraint optimization scheme. But besides the first time experiment that I did that was 500 time steps long, I also looked at doing another time step or another collection of experiments from time evolution. And that was really showing that we can also take a 500 time step evolution and we can look at different values of L or either X, namely different values or different possibilities for the length of the entire domain that we're trying to perform time evolution over, in addition to each one of the points X, which is representing every one of the points in space on the Cartesian grid at which we would like to determine the solution from this well-posed initial value problem for the PDE. And I just really exhibited that you can test out many types of parameters and which were exhibiting different types of solution curves that were included in my preprint. Some of them I looked at just linear functions or quadratic functions, and I think that at least for a naive type of application, it can be helpful to look at those types of characteristics of the solutions. Now, obviously, realistically speaking, from more of a philosophical point of view, it can be difficult to determine whether this type of quantum algorithm could be used for gathering readout from more complicated nonlinear problems. I think that personally, it would be really hard to determine whether, say, there are different types of initial conditions that could be passed, or or um or there could also be, any types of difficulties associated with the optimizers. For the Kamasa Home PD or the Benny Luke PD, I really heavily required upon the Nevergrad optimizer. But in this case, for this type of PD, there was also there was also different types of difficulties associated with performing time evolution, which were easiest to do with the PySwarm optimizer. The PySwarm optimizer, it's another type of optimizer which is used from initial conditions of PDEs. And what this has the effect of doing is that the PySwarm optimizer was able to, in my opinion, in some time experiments, be able to more quickly perform the time evolution than the Nevergrad optimizer. And I mean, that goes to show about how the components of algorithmic design and looking to see if there was some classical or quantum next generation processor which could be used to carry out these algorithms, how it would be dependent upon the processor itself. Because I can just speak that for in some cases, it can just be difficult to sort through all these possibilities. But inevitably, when you're trying to look to run an algorithm or you're trying to look to pass different initial conditions to an algorithm, that's going to be what you're having to do. And in this case, as I kind of alluded to, but I want to get more into now, just in comparison to say the Benny-Luke equation or other types of equations which you can use this quantum algorithm to solve for to further investigate and time evolve. It's just really demonstrating that how different components and different pieces of the algorithm would have to be adjusted and what's the ambition and the different types of expectations that someone would have, and you would have to list out and write out in the cost function. And but as a superposition of expectation values, it's not really helpful in itself just to be able to analytically derive the cost function, because you really have to determine and think clearly about or convince yourself about which types of initial conditions would be the best to use. And in this case, I kind of motivated clearly the fact that when you have to make use of different types of initial conditions and looking at the ansatz for the two components and the two solutions to the PDE, there can be different types of ways to think about how maybe sinusoidal information or sinusoidal initial conditions from the Kamasa home PDE can come into play. And even though the fact that the Benny-Luke equation, like I had expressed, I think that, in my opinion, from an algorithmic perspective, it's a lot less tractable on near-term hardware. It's still helpful to think about even which types of initial conditions are passed to that system, because when you try to maybe pass an optimization budget or a budget parameter to your optimizer that is too small, it can result in a very large polynomial overhead in terms of the runtime that your algorithm needs to even explore the initial state of the configuration of the ansatz in Hilbert space. And this is even just another collection of experiments that I perform with 500 time steps, and then these are just all of the plotting. So all of the plotting is just really using the same types of functions that I used earlier. And yeah, I have some other types of ideas for some other scripts, which I'll just be talking about more in these types of presentations soon. But thanks for watching.